So thank you very much for this introduction, and thank you very much to the organization who made this conference happen. Today I would like to speak about some new results on one-point functions in the supersymmetric sine-Gordon model, and this work is based on this paper done during my PhD with Fyodor Smirnov. So, first question, what is a supersymmetric sine-Gordon model? So this is a two-dimensional integrable supersymmetric quantum field theory. And our main quantity of interest are the one-point functions. So why? This is for two reasons. First, because they are with the structure constant of the quantum field theory, the main ingredients in the operator product expansion. And second, the one-point functions are purely infrared data. That means they are not accessible by usual perturbational techniques of quantum field theory, which is our main tool. So we need to develop some alternative, new and systematic approach for the calculation. So basically such approach exists in the specific case of the sine-Gordon QFT and goes by the name of the fermionic basis. So this fermionic basis has been developed in this series of papers, the hidden Grassmann structure paper, by this group of people. So Bose, Jimba, Miva, Tekiyama, and Smirnov. And this hidden Grassmann structure story started with the study of the factorization property inside the lattice 6 vertex model, which is the lattice regularization of this sine-Gordon. So basically, our problematic here is the following. We'd like to go through the steps of the usual fermionic basis, but apply it to a more complicated theory, we'll say a higher spin theory, which in our case, on the lattice side, will be the 19 vertex model, and in the QFT side, this will be the super sine-Gordon model. So to do so, I will first sketch the methodology of the usual fermionic basis. So basically, one claims that we have two operators, B star, C star, that lives on the lattice. And then when they act on some lattice primary field Q alpha H in such a way, they form a basis of local operators. And this basis is powerful because the lattice vacuum expectation value is given by just a single determinant of a function omega that was already mentioned yesterday by Frank. So then, basically, in the hidden Grassmann structure 4 paper, one claims that this B star and C star operators, they have nicely defined scale. Question? The what, sorry? The P, this is the number of C's and B's. Just this is the size of the determinant. So these B star and C star, they have nicely defined scaling limits in the QFT, okay, that we call beta star and gamma star. And moreover, such type of vacuum expectation value, they scale nicely to some one-point functions in the QFT side that corresponds exactly to this operator beta and gamma. So now you understand that if you have a scaling equation on the function omega, that is, if you can get the behavior of omega at the level of the QFT, then by a numerical study you could access such quantity. And then in 13, there was a last step in this procedure done by Negre and Smirnov, which used the compatibility of the reflection relation and the fermionic basis to somehow recover independently this last result. So what I would like to do today is first to present you the super sine-Gordon QFT and show you the results that we got. And then, basically, as you understood, there are these two ways of proceeding to one-point function. Either you go from the lattice towards the scaling and you get the one-point function as a numerical study of the scaling equation, or you use the reflection relation and its compatibility with the fermionic basis. Today I will mostly speak about this first part. So we'll be interested. So first, I will show you the results, and we'll speak about the 19 vertex model so I will speak about the 19 vertex model, and as I said, we want to generalize this fermionic basis approach, and this has already been done at the level of the basis itself by Jimbo, Miva, and Smirnov in 14. And they have introduced this spin 1, we'll call it the fermion current basis. So bold letters now mean spin 1 operators. And now, in addition to the fermionic part, there are also currents. But we, in this talk, will be interested only on the fermionic part, this bold B star, bold C star. And we will construct the simplest vacuum expectation value that we can imagine at all, just an action of bold B, bold C on this lattice primary field, and we will call it omega. And the main objective of today is to derive a scaling equation on this big omega. So let's start with the super-Sine-Gordon quantum field theory. So as I said, this is two-dimensional integrable supersymmetric quantum field theory given by this action here. So you have two fields, bosonic field phi, fermionic field psi, some interaction term which is parameterized by this parameter beta. And the way we treat it, we consider that this quantum field theory is a perturbation of the complex super-Liouville conformal field theory, which is just this first bracket. So this CFT has a specific central charge C, okay, which is parameterized by this beta, and its primary fields are given by such a vertex operator with this specific parameterization. And this, in turn, gives us the following formula for the conformal dimension of this vertex operator. So we have this conformal field theory, which is here. We perturb it by this last term. So this perturbation is relevant. So we get a massive theory where the mass is related to the coupling constant by this TBA formula. And finally, the super-Sine-Gordon theory, as we said, is an integrable field theory. That is, there is an infinite set of integrable densities that we call T2K. And out of these densities, we can act on local field. So how? Basically, we just multiply the density with the local field O, and we integrate around the location of this field. Now, the usual geometrical setup of the fermionic basis is the cylinder. So we make our theory live on the cylinder of radius r, and we put our field of which we want to compute the one-point function at the origin, and with the following boundary conditions. So at the two extremities of the cylinder, we take two primary fields of conformal dimension delta p. So this delta p is parameterized by this quasi-momentum p, which is really our boundary condition. And now you can see that with such same boundary conditions at the two extremities, basically with the one-point function of such fields, of the action of local integrals of motion on fields, is 0. And this is important, and means that everything that we are doing is done modulo the action of local integrals of motion. And final important formula here that claims that if we properly normalize the one-point function in the quantum field theory, that is by the radius to the power of 2 conformal dimension of this field, and we take the 0 radius limit, we recover the one-point functions of the corresponding field, but in the conformal field theory. And this formula will be used when we want to match the results from the scaling equation with the result coming from the reflection relation approach. So now I can show you the result that we obtained. So the one-point function, we call them big omega with these indices, and these are just these two operators, beta star, gamma star, acting on the vertex operator V alpha. So this beta star is the limits of this bold B, this spin 1B, and gamma star is the limits on the QFT level of this bold C or spin 1C. And then you can see the first of these one-point functions. So they are all even polynomials in the quasi-momentum P, our boundary conditions. And the degree of the polynomial is equal to the sum of the indices. This number, we call it the level. And the coefficients, these are polynomials in the conformal dimension of the primary field and of the central charge C. And finally, there is a last piece. So you notice that if you swap the indices, you just make appear extra minus sign in a term which is controlled by a function that we call D, and that will be explicited later. So this is just some first one-point functions of the first fermionic elements. But what is really the main output of the paper is the scaling equation on this function omega, with which a priori you could extract any one-point function. So let's now talk about this. That is about the lattice, the 19-vertex model, and the lattice scaling equations. So as for the QFT, we consider a cylinder on which we wrap this 19-vertex model. So here are a couple of words of terminology. So this will be called the space direction with n sides, and this is the Matsubara direction with L sides. Here on each line you have an inhomogeneities to J. When you go around this cycle, there is a twist kappa, and there is the parameter of this 19-vertex model is called nu, or also you will see Q. So you have this cylinder. There is this 19-vertex model which is wrapped along this cylinder. This model is integrable, so it has this R matrix. So it's 9 by 9, which is normal because it's a spin-1 model. And the weights are summarized below. And here you see stuff of the form plus minus pi I over 2. And this is actually natural because it is known that the 19-vertex model is a fusion of 2 6-vertex model, and we will also see this behavior on the level of the fermionic basis. So now let's start by defining what we mean by a vacuum expectation value on the lattice. So first, we define the Matsubara monodromy matrix. So as usual, you just multiply the R matrices along the Matsubara direction. If you twist and you take the trace, you get the transfer matrix. And then, if you allow for this space, for the auxiliary space to be of spin 1 or spin 1/2, you can have two ground state eigenvalue that we denote T1/2 or T1. Then there is this total monodromy matrix. Just again, you multiply the R matrices along all the cylinder. And finally, we define what we mean by the lattice primary field is Q power alpha H of 0. In which way? So HK is just a Cartan generator of SL2 acting on side K. Then you have the simultaneous action, and out of which you define this lattice primary field. And now we are ready to define the vacuum expectation value of a local operator O by this formula. So it's just an infinite cylinder limit of double traces of the transfer matrix with the insertion of the operator O. So this is a kind of natural definition because this is more or less the partition function of the model. So this is the partition function with the insertion of the operator O, normalized by the partition function. So now, if you take O to be some random operator, there is no hope that you will be able to compute this. But hopefully, there is the fermionic basis. So in the case of the 6-vertex model, as we have seen, there are this operator B star, C star, that when they act on this lattice primary field, they are given just as a determinant of one function. And this function is characterized uniquely by the Matsubara data, that is, by what's going on this compact direction. But our case of study is a 19-vertex model, and we are concentrated on these fermions, okay? And basically, in this paper of 14 of Jimba, Miva, and Smirnov, they derived some fusion relations between the two bases, the spin 1 and the spin 1/2. And in our case of interest, they are written in this equation 3 and 4. That is, the two spin 1 fermions on the left-hand side, you can express them as sums of spin 1/2 fermions with this shifted argument that we have already seen, plus minus pi I over 2. And there is this normalization factor built out of this ground state eigenvalues. So now, our main object of interest, as we have already seen, is this omega, vacuum expectation value on the lattice of these two fermions acting on the lattice primary field. And now you see that if you insert 3 and 4 in this boxed formula, and you use this equation 2, just for B and C, there is no determinant, you can express the big omega as a sum of 4 shifted omega. And now, basically, the main part of the job was to using all the information that is known on this function little omega to derive a scaling equation on the big omega. So I will skip all the details, I will just show you the results, but before I need to introduce some more definitions. So first, this Baxter function Q, which is just a trigonometric polynomial of the beta roots, again in the Matsubara direction. Then there is these two functions A and D, the function from the TQ relation, and then the product that we call F. So first, to have the scaling equations, we need to define the function Y and B. So Y is just a normalized spin 1 eigenvalue, and B is just a ratio of Q multiplied by this T1 half with some more stuff. Then we need two kernels, one which is just L 1 over hyperbolic cosinus, and then there is really the kernel of the model, the G alpha, which is this integral kernel, which depends on alpha, the weight of the vertex operator, and the beta, the parameter of our field theory. So now these two functions, Y and B, we can write functional relations among them. They come from a TQ relation, fusion relation on the lattice. Then we take this functional relation and we put them in an integral form. And in this integral form, we can take the scaling. So technically, the scaling limit means that we take alternating inhomogeneities and we send them to infinity, together with the length of the Matsubara direction taking to be infinite, and keeping this product going to m times r, the mass and the radius. So since we go from the lattice to the field theory, you have a relation between the lattice parameter and the QFT parameter, and the twist becomes just the quasi-momentum P. So in a paper of 3 years ago, we managed to write this scaling equation for the function log y and log b, so as they are summarized here. And you see that this boundary condition appear in this driving term together with this mr parameter. And now basically what we did in this last paper is that we used these two equations to derive a scaling equation on the function big omega. So it's written here. So first we need to define these three measures built of these two functions b and y, so dmb, dmb bar, and dmy, which have all the same structure, basically b over 1 plus b. And the scaling equation on the function omega is written here. So inside you have L, which is this simple kernel. You have the measure dmb and dmb bar that you can get by solving the equation on log y and log b. And there is this function g and g bar. And these functions g and g bar, they satisfy the same type of scaling equations which are coupled to big omega. So these are these two equations, and they depend on the kernel G alpha, of course on omega because they are coupled to it, and on the measure. So now that we have this, it means that we have the function omega on the level of the quantum field theory. And we can start to solve them. So as I said, what we're interested in is matching these results from results that will come from reflection relations, and this is done in the conformal regime, that is when we take this product exponentially small, okay? And in this limit, we assume that our function omega has this asymptotic expansion, okay? Let's call it roughly a Taylor expansion, that is First we have the variables, then we have a function d that appears twice with a shifted argument here. This function d has to be found. And then there is really what we mean by a Taylor coefficient. And this Taylor coefficient is really what we expect to be a one-point function of some local operator. So now what we did, so we have these scaling equations on function big omega. We coded them on a computer. Then we took this Taylor expansion, we plug it inside our code, and then we numerically solve it, and by interpolation we were able to first identify this function d. So this is given here by this ratio of gamma function. And then we were able to compute the first Taylor coefficients omegas, okay? So remember that there was this function d, its expression again found by interpolation is this. And here I come back to what I showed you at the beginning, that is the first fermionic one-point functions. So here, basically we managed to compute only the first 4 because we are limited by the power of our computers. But in principle, since we have this scaling equation, one could compute any such fermionic one-point function. And now, if you look closely at the result, you can see that basically these fermionic one-point functions, they have all the same structure. You can write them as polynomials, which are controlled by this function d alpha, which controls this swap of the indices. Polynomials in the super Virasoro modes that act on the vertex operator. And this is why? This is because basically if you compute a one-point function of a super Virasoro descendant in the cylinder, they have exactly this form of a polynomial with a polynomial dependence on the conformal dimension. So this observation, the fact that these types of fermionic operator, beta star, gamma star, can be rewritten as super Virasoro modes, is the first observation to start this reflection relation approach. So now I come to the end of my presentation, and I just want to say that now that we have this scaling equation on omega, we can in principle compute any one-point functions of this form. So here I plus, I minus are just multi-indices, and such quantity is just the determinant of the corresponding Taylor coefficients, okay? Now, this check with the reflection relation, this is what we did in the second half of the paper. And this is, as I said, a completely independent approach. And the fact that the two converge to the same result is a strong argument in favor for both of them. And of course, the next step in the study is to understand how behaves this current contribution, J. And once this would have been understood, the full integrable structure of this model will be got. So, thank you very much for your attention.
Thank you, Constantin. If there are questions, or everybody is thinking of the coffee break already. Okay.
So, can you really calculate the one-point functions or ratio of one-point functions?
No, of course you normalize by just like here.
Yeah.
By the
Yeah.
I don't. Yeah, here, not here. Yes.
Yeah, but in the last slide you didn't normalize.
Okay, but it just where you mean here? No, but it's just a matter of notation to keep it clear. But of course, there is always this factor 1 over v. Yes.
Yes, but if you are in a finite volume, finite capital R,
yes,
then the quantity which you normalize is also non-trivial function of R.
Yeah, sure, yes. But the goal is to match on the levels of the conformal field theory, these two bases. So
could be a rule that you calculate for any R, the one.
yes, sure, but by this approach, I don't know how it could work. But yeah. Mm-hmm.
So I agree. Compared with the very small volume expansion,
yes,
and compared with CFT, but you could also compare with very large volume expansion.
Yeah, but this is okay. Mm-hmm.
Also interesting. Or infinite volume form factor, scattering data, finite size correction.
Yeah, but in the paper there is another comparison. I think it's somewhere in the talk, maybe. I don't remember well. So you can do another. Yeah, I think it's here. So it's still conformal, but you can take another limit here, and then basically you end up with that your fermionic one-point function, it scales to this type of field. So it's still conformal, but it's a bit a different application. And here you see there is a different fields that enter into the game. So it's not just restricted to this case of descendant of Super Virasoro.
So you mentioned the relationship between the fermionic basis and the Super Virasoro. What is known about this relationship, or is it just
But it just basically, like I can show you some examples. Sorry. So the simplest example is at level 2. So this is what comes from the reflection relations. So we have this, the simplest one that we got. And basically you can show that, for example, at this, when you take it inside the CFT, in the CFT, they decompose on the Virasoro basis, in the Super Virasoro basis in such a way. Basically, the claim is that you can do it at any level. And we did it for all fermionic one-point functions that we have found.
And this is one of the very interesting non-solved problems even for the usual sine-Gordon case. How to express this in the CFT limit, how the transform of a base from the Virasoro basis to the fermionic basis. And it is only known for the first, I don't know, 8 levels.
Yes.
With that. But for the super case, of course, much less is known. It's a very interesting question. But I think nobody knows.
I was asking because I wanted to know if something systematic can be.
There is just reflection relations, which seems to work the most powerful method to get the correspondence between the two. But there's no general formula.
So in the sine-Gordon case, sometimes it can happen that you act with this beta gamma system and you don't get a descendant, but you shift the weight of the vertex operator.
But this is this is like here, right? I think. Yes, but this is this formula. So you have this beta star gamma star, and then you have this field, and you shift it here. Mm-hmm. So yeah, you get the same stuff.
Maybe I ask one question before we go to break. So how about the inclusion of the integrals of motion here? Is there any hope or?
I think it's still an open question, and I don't know how to do it also. Yeah, still on the list of problems to solve.